Hello, everyone. Thank you so much for coming to our weekly seminar series. Today, the Invertebrate Ecology Lab is hosting Dr. Mike Vardaro, who's visiting here. Dr. Vardaro currently works at the Ocean Observatories initiative, but prior to working there, he studied links between surface productivity, carbon flux, and deep benthic invertebrate populations, and how such systems change over time. And so he did that by designing and deploying photographic and oceanographic instrumentation in a variety of ecosystems. During his master's at Texas A&M, he studied in the Gulf of Mexico. Then he moved on to the Northeastern Pacific during his PhD at Scripps Institution of Oceanography. And then he was a postdoc at the Monterey Bay Aquarium Research Institute just down the road. And while he was a postdoc, he actually worked in southeastern Atlantic oceans. There are stories from that, to recall. So not in this talk, and a future talk, a happy hour talk. So Mike has worked with the NSF Ocean Observatories Initiative since 2011. He started as a project scientist at Oregon State University, focusing on designing, testing, and deploying the Endurance Array off the coast of Oregon and Washington. He was Ocean Observatories Initiative data manager at Rutgers University, working with the cyber infrastructure team to monitor and evaluate quality control data streams for the user community for OOI data. And he's currently a research scientist with the University of Washington on the Regional Cabled Array, which streams real-time data to shore from a network of 150 diverse instruments that span the Juan de Fuca tectonic plate. And he is, in addition to all of that, a marine science lecturer at San Jose State University and has been since 2020. So some of you may interact with him that way as well. So with that, I leave him to tell you all the exciting stuff about this. So please join me in welcoming Dr. Vardaro for talking about ocean observatories, open access to the open ocean. It's a lot of O's.
It is. I didn't think about that. Thank you. It's good to be here, and thanks, Amanda, for the invitation. Yeah, I didn't realize you were going to give such a detailed introduction, so that sort of obviates some of this first slide. But the money for the Ocean Observatories Initiative has moved around a lot, as have I, over the course of my career. So I'm from Philadelphia, so if I say water occasionally, that's why. I went to school in DC, got my master's in College Station, then San Diego, then did my postdoc at MBARI, and then yeah, moved around as part of the OI. So now I'm in San Jose. So yeah, for my master's research, I studied methane seep communities in the Gulf of Mexico. This was my first little camera that we helped deploy. Looking at a gas hydrate mound here. There's bubble plume here. We'll talk more about methane hydrate on this in this talk. I got to go in the Johnson Sea Link submersible as part of that. That was fun. And then I moved on to studying deep sea invertebrates like this deep sea urchin, Echinocrepus. I didn't manage to get this into the talk, but I always like to include this little video that we shot that shows that. So I was looking at carbon transport from the surface to the seafloor and bioturbation by these little sea urchins. This is super sped up. This is one picture every, I think, 5 minutes over the course of a day. And I like to include this because it shows the bioturbation, and also because my friend could not stop laughing at the orange nose on the seafloor and had to leave my defense. So anyway, that plays for a little while. But and then I joined the Ocean Observatories Initiative in 2011 as a project scientist, and started working on this project. This is the cabled array, which I joined in 2018 when the money for project science moved back to University of Washington. And it's a very exciting part of the OOI. And I will speak louder because people can't hear me. So anyway, one of the things that we have is an HD camera, and I'll go into that. This is at axial seamount, and it's looking at a hydrothermal vent community. So this streams data back in real time, 24 hours a day. Not the camera, but the array is streaming back data 24 hours a day. So anyway, I will go into some ocean observatories science. So I'll talk a little bit about the history of ocean observatories and ocean observations, and then talk about OOI, and then talk a little bit about some in-development technology and PI projects that are using OOI infrastructure and OOI data. So as you know, ocean science still relies on ships for a lot of the work that we do. We go out, we drop instruments off, take observations, and then come back to shore. Our reach has been extended by submersibles of different types. They go deeper and deeper and deeper. This now includes robotic submersibles, AUVs, gliders, and combination vehicles like Sentry that are ROVs and AUVs. And our ability to map the oceans has also been extended over the course of the century with new technologies, echo sounders, multi-beam sonars, and even satellite technology that lets us look at gravity perturbations, that let us look at seamounts or sea-buried tectonic structures. But if you want to look at how things change over time, you need a long-term presence in the ocean. And so the Ocean Observatories Initiative, as one of these observatories, it's a similar concept to a terrestrial observatory, where you're looking at something much closer over a longer period of time. They're more limited by the physical and chemical properties of water, in that light doesn't travel as far. There's localized currents and chemistry and productivity. You can get contamination over time and corrosion because it's a very high pressure environment. And so you have to build things to withstand these conditions. And these observatories can take the form of anything from underwater habitats, which is how some of these started, buoy systems and instrumented moorings that have instruments that go down below the surface, look at atmospheric flux and other properties at the surface down through the water column. The Deep Ocean Drilling Project has instrumented boreholes and put observatories down that look below the seafloor. So that Cork program began in 1981, and they examined the geological and hydrological state of the ocean crust. And then you have things like Lagrangian floats, the Argo program, observatories that look over the entire ocean, but not in one particular place. The floats move with the currents, and so you get a wide-scale view, but maybe not the deep, long-term time series that some people would be looking for. And if you want that type of thing, you could use a cabled observatory. The first one was established off Japan in 1983. The second was the H2O Observatory, midway between Hawaii and California in 1988. There was one next door, the Mbari Mars Observatory. Aloha, Neptune, and Venus, which initially were part of the OOI, and then Canada got their money first, and so they deployed the Neptune and Venus observatories in 2009. And then the Ocean Observatories Initiative, part of which is a cabled array, which went operational in 2015. So, what is OOI? OOI is a series of 7 arrays. 5 of these are active in the northern hemisphere. The southern hemisphere, unfortunately, became too expensive for NSF to operate. This is all funded by the National Science Foundation, which was part of the reason why they're there. It's expensive and difficult to get to these places, and so there are few long-term time series there. So the data from these are still online. They were deployed and operated for a number of years, but are now unfortunately offline. But we still have these. The Pioneer Array off of New England has now relocated to the Mid-Atlantic Bight off North Carolina. But the other ones are still in the places that you see on the map. There's a number of different stable platforms and mobile assets, and the stable platforms include seafloor nodes. I'll go into some of that. Lots of different instruments, over 2,500 core science data products, and then over 100,000 associated engineering data products. That's sort of an artificial distinction, but there's a lot of data is the point. And it's all open access. And you can go to oceanobservatories.org if you want to check it out. There's also a dataexplorer.oceanobservatories.org, which is the portal. That was the QR code that I'll show again at the end. So the OOI was designed by a committee of scientists who came together to form this, to answer 10 basic scientific questions, to address 10 scientific questions. I don't know if that we've come up with the answers in the 10 years that it's been in operation. And everything from climate change and ocean acidification to gas hydrates and seismic activity. So this covers many different time and spatial scales, from surface storms and surface to seawater flux of CO2 and other greenhouse gases, down through the water column to the subsea floor, looking at seismic activity and gas hydrates and other processes down at and below the seafloor. So, what are the benefits of these long-term observatories? We get abundant power because the Cable Observatory in particular has an electro-optical cable that delivers constant power and data back to shore. The buoys have solar and wind generation and significant battery packs that kept getting larger and larger, so the buoys kept getting larger and larger, but abundant power. Real-time and near real-time data via the cable and via telemetry to shore via satellite. Shoreside monitoring, so we know when things go offline. If you go out to sea and you deploy equipment, you don't always know whether it's doing what you want it to do. With this, we do know whether it's online, and we can sometimes take action if there are changes in functionality. We can change the sampling program. For instance, I showed the axial seamount earlier. We'll talk about that more, but it's a volcano off the coast of Oregon that's on the verge of eruption. So if that does happen, the sampling program at axial will change significantly. New sensor developments. So there's PIs that are attaching instruments, and they can expand the observatory and include new in-development technologies. And it's a consistent long-term presence that allows for a lot of different observational and experimental programs. The challenges are developing and deploying all of these moorings and gliders and cabled sensor packages. It's a lot to keep track of, 24 hours a day throughout the year. It's deployed at a limited location, so unlike an Argo float, you can't observe the entire ocean with a seafloor observatory. The sensor and node maintenance over these long deployment times, you can't always go back out there initially or immediately and fix things if things do go wrong. Designing novel sensor types, which was a benefit, is also very difficult, and making sure that they can plug in and play well with the network is sometimes difficult. And that includes repurposing some sensors to connect to the power and data lines. Coordinating with the global science community. You're not always collecting data at the sampling rate or in the format that every scientist is going to want. And so you're constantly getting feedback and trying to make changes, but not, breaking things or breaking the time series for everybody else. And then analysis of all this data. I'm part of the data team at University of Washington. There's a data team at Woods Hole that's working on the Pioneer and Global Arrays, and then there's a separate data team at Oregon State. And it's only about 10 people total for all of these sensors and data types. And so, as some people have said, with observatories like this, you're drinking from the fire hose of data. And then presenting all this data in a standardized way, in a single location, so everybody can get what they're looking for from a single spot. Okay, so the different arrays, there's 2 global scale nodes, Erminger C and Station Papa. These are sort of a triangular array of moorings and profilers with gliders that go in between. And this was designed to look at storms, air-sea flux, currents, turbulence, temperature, oxygen, a lot of different global scale phenomena. The Pioneer Array, which, as I said, used to be off of Martha's Vineyard in New England, it was this sort of array, a similar type of array of moorings and gliders and AUVs, including wire-following profilers, surface buoys, different nodes with sensors on them just below the buoy and all the way at the seafloor, the profilers going up and down in between. This has now been redesigned and moved to the Mid-Atlantic Bight. There's a long process where they took proposals of where to move it to, including some people wanted to move it to the Gulf of Mexico, other people wanted to put it in other interesting locations. So now it's off the coast of North Carolina, north of Cape Hatteras. And it has some new mooring designs, some shallow water moorings with crawler profilers, similar to the wire crawling profilers that we had earlier. It also has a flow cytobot on it now, so they're taking plankton measurements. And that is being incorporated into our data portal. It's generating a huge amount of data, and so we're working to get that online and to people. And then there's the Endurance Array, which is off the coast of Oregon. This is another coastal array. You can see the cable on here. It's sort of the cabled array and the Endurance Array were sort of designed to be co-located. The southern line of the cabled array comes around here back onto the shelf where the Newport line of moorings and gliders operate. And then there's the Grays Harbor line up here, so shelf, inshore shelf and offshore moorings at these two locations, north and south of the Columbia River outflow. So this is monitoring that river outflow as well as ocean acidification, hypoxia events, and a lot of different cross-shelf and along-shelf behaviors and phenomena. What else did I want to say about that? So there's these 6 Teledyne Web Slocum gliders that follow roughly this pattern. It's been a little bit challenging to keep all 6 of them operating continuously in this location because there's a lot of currents, and the freshwater outflow makes it challenging to fly them sometimes. But yeah, so this is operated by Oregon State on the West Coast. And I forget if I mentioned this, Woods Hole is operating the Global and the Pioneer Array. And then there's the group that I belong to, the Cabled Array, and I will focus a little bit more in depth on the Cabled Array because that's the one I work for. So there's the 900 kilometers of high bandwidth, high power primary cables on the seafloor. They come out of Pacific City, Oregon, and there's the northern line that goes out to axial seamount, and the southern line goes back around to Slope Base, Hydrate Ridge, and then back onto the shelf near the Endurance Array. So there's 18 junction boxes that step down the power and provide power to all the instrumentation. 6 instrumented moorings with wire crawling, some shallow profilers and some deep profilers, and then over 140 instruments that provide 24/7 real-time data and status tracking with two-way communication. And it's expandable, so we have open ports that people can plug new instrumentation into to get new types of data back and do new types of experiments. We do 35 to 45 day maintenance cruise every year in order to turn the instruments around and pull up nodes or moorings that might need to be refurbished. We use Ropos and JSON submersibles, and UW students and sometimes external students come along to do the work. Not the work, they come and help us with the work. They get to experience all aspects of seagoing research. We also do the work. But they're directly involved in the ROV operations, and they get to work on water sampling and other types of science that we do at sea. So these are the main science themes that are addressed by the core cabled array, RCA's Regional Cabled Array Infrastructure. There's a lot of acronyms, so if anything is unclear, just raise your hand and I can try to answer the question. So yeah, climate variability is looked at primarily by the profilers, also looking at ocean food webs, biogeochemical cycles, coastal ocean dynamics, fluid rock interactions and subsea floor biosphere, turbulent mixing, global and plate scale geodynamics. And so there's a lot of sub-questions that go along with these major science questions. This is a sort of a schematic of what the array looks like on the seafloor, including the profilers. There's these big 2-legged moorings with platforms and a little profiling pod that goes up and down between the upper 200 meters and the surface, near surface. And then the glider lines are more inshore, part of the Endurance Array. So anyway, the cable spans 2,900 meters to 80-meter water depths. So this is sort of what these profilers look like. And they take profiles through the water column from near surface all the way down to the deepest sites at axial base and slope base. This is the little coffee cup contraption that the ROV holds to clean the cable every year. And the fish come around. These are black cod, frequently seen at the Oregon offshore site. they come around and see what we've scraped off the cable as we go up and down. So this is the profiler pod coming into dock at the 200-meter platform. So this is, it's hard to get a scale here, but it's sort of minivan sized. And we can pull it back onto the ship to refurbish it. And there's two pods on either side that the ROV can dock into and pull the profiler pod back on, and then an instrument package on the other side. And then these guys can pop on and off the cable with a latching mechanism that the ROV can operate. So we don't have to pull the whole mooring in to refurbish it. And these profilers have provided us with nearly a decade of full ocean depth, high resolution measurements of a lot of different processes, but ocean acidification is one. PCO2 measurements. We also have pH measurements. There's a whole suite of sensors on these profiler pods, including oxygen, temperature. And so you can put these together into profiles, and we look at this data and try to quality control these so that people are getting the data that they want. So there's the 3 cable cello profilers on the moorings, and then these co-registered PCO2 measurements from 18 different biogeochemical and physical instruments. And yeah, high resolution, nearly continuous record of CO2 to full ocean depth. And that was not the button I meant to hit. We also have hydrophones. Apologies for the annoying sound. That is the ADCP pinging. But we also get whale sounds, anthropogenic noise. There are hydrophones that are at the Oregon offshore site, the shelf site, and some on the platforms, and some down at slope base at 2,900 meters depth. So the hydrophone data over the past decade shows fin whale songs have been changing over time, becoming quieter. A UW student analyzed 143,000 different whale calls at axial and slope base over 5 years. And there wasn't a lot of prior data to compare it to, but they did manage to compare it. And it seems like they arrive at the base of the Cascadia margin about 2 to 3 months earlier than they do at axial seamount. We're not sure if they're following prey, but that's, there's a lot of different projects that could be enabled by the hydrophone data. And this, again, is all open access for people to look at and listen to. And we're still working on a new interface that will let people access and view that more easily. Sorry about the annoying noise. Methane seeps are also a significant environment along the Cascade margin. They're a geohazard, but there's bubble plumes that are releasing methane into the water column. This potential energy reserve, also a greenhouse gas, creates slope instability, creates essential fish habitat. And so our observatory is sort of connecting the seafloor to the hydrosphere. This was enabled by a bioacoustic sonar that was deployed by a group in Germany, looking at the methane plumes, and then you can see krill and phytoplankton, or zooplankton in the water column. So yeah, there's exposed methane hydrate at this site as well, which is somewhat unusual. Methane hydrate is an ice that forms under high pressure, low temperature conditions where methane gets trapped within a lattice of water molecules. And it's not entirely stable when warm water comes through. And so it releases these methane bubble plumes, which sort of bubble up from below, naturally forming methane. And only a few places in the world like this are instrumented to the degree that hydrate ridge is. And so, yeah, the direct link from below the seafloor to the shallow hydrosphere, and there's teratons, trillions of tons of methane that are trapped below the seafloor around all continental margins. And so understanding these environments is key to climate models and also interesting to a lot of different fields. So in addition to that, axial seamount is also part of the cabled array. It is the most advanced submarine volcanic observatory. Over 70% of the volcanism on Earth occurs underwater in systems like this. It emits huge amounts of heat and chemicals and biological material to the seafloor, but it's poorly studied over time. We sometimes don't find these until they erupt, but this one is known to exist and is now fully instrumented. So this is some ROV data from one of our cruises, but you can see the superheated 300 degrees Celsius water emanating from the hydrothermal vents there. So there's these underwater hot springs that are extreme environments that also host unique organisms, tube worms and limpets and all types of different polychaetes. And Axial is the largest and most magmatically robust volcano on the Washington-Oregon coast. And so we've been studying this since the OI was put in place. This is the eruption in 2015. These are all earthquakes that were observed by the seismic sensors, clusters of over 8,000 earthquakes in 24 hours. And the seafloor dropped by a few meters. In 2015, April 24th, 2015, the seafloor dropped as the lava erupted onto the seafloor and the magma chamber collapsed. And so you can see this in the bottom pressure tilt sensors that we have at Axial. We also have those at Hydrate Ridge to look at instability there. So you can see that the magma chamber has been inflating since that eruption. And so we're looking to see if we can predict when the next eruption is going to occur. So you can see increased seismic activity here. This is the depth that the seafloor was when the eruption occurred in 2011. This is the depth when the 2015 eruption occurred, and we reached that in October of this year. And so they're looking to see if maybe it's going to erupt in the next year or so, possibly 2 years. This rate of increase has actually leveled off a little bit, so they pushed the prediction back a little bit. But people like Bill Chadwick at Oregon State and other people are looking at these data and trying to predict exactly when the eruption is going to occur. But we know it's going to happen. And then we have things like the HD video camera. This is pointing at the mushroom hydrothermal vent. High definition video streams from this every 3 hours for about 15 minutes, every day. So we're getting real-time video back from 300 miles offshore. I was looking at the video one day and happened to notice this octopus that came in for a spa day or something. I'm not entirely sure why it's sitting on the top of the hydrothermal vent. Again, this is 300 degrees Celsius fluid, but it seems fine. And it swam away, so it didn't get cooked. But yeah, so we're looking at long-term characterization of life at these vents. And what occurs here, this little vent is actually fairly new. This popped up right in front of the camera. Hopefully it doesn't get any closer to the camera or the cable. And we're not entirely sure what's going to happen when the eruption occurs, but things do seem to be heating up there over time. And, oh, it started over. Okay, so that's sort of an overview of the observatory itself, and then what types of research does the observatory enable, existing and in development technologies. So this is an instrument that was deployed by scientists at Rutgers, as well. There's a group that's behind this, but it's the COVIS, kind of poorly named. It was deployed right before COVID came in. But anyway, COVIS, the vent imaging sonar, it maps heat flow and sort of quantifies the vent field by looking at the way that sound waves travel through the water as it heats up and cools down. So it's looking at diffuse heat flow over the seafloor. And they were able to look at sort of diffuse flow around the vent. This is the Inferno vent. COVIS was right in front of it, in between Inferno and Mushroom. Mushroom is where where the HD video camera is. And so they looked at heat flow over several years. This has now been recovered, but may be deployed again in the future. The MEREM group in Germany deployed a sonar at Southern Hydrate Ridge. So this is an echo beam, multi-beam echo sounder that can rotate. So it gets a 360-degree view, 256 beams, many different frequencies. And then the files were sent back to OI and then synced to Bremen for real-time post-processing. Not real-time, post-processing. So yeah, they were able to put this together and look at these methane bubble plumes and see how the methane emanations change over time. And they could see blowout events where that gas hydrate destabilized and created pockmarks and collapses. They also had a 4K camera that was deployed here. You can see this hummocky material. This is all sediment on top of exposed hydrate and carbonate rock. And so this little crevice here, so they were looking at the size of the bubble plumes over time and correlating the image data with the sonar. And you can see over time, so they put this little measuring stick here in the crevice, and you can see there was collapses. And so this site is very unstable, and so things that we put in place one year are not where we put them the next year when you go back. And so it's an interesting place to study and to deploy instrumentation. There's other more experimental sensors like this benthic observing platform that Claire Reimers at OSU and Pete Gerges at Harvard deployed, which is a bioelectrical energy device. So the idea was to generate power using a microbial fuel cell. And so there's a little incubating chamber here that they sort of fed the microbes and then used the microbial activity to generate electricity. And so they incubated these seep sediments in high pressure reactors to establish the response, and then they used that to power, fill these batteries and then power at CTD. And they were able to trigger water pumps and record data using this fuel cell. And this was deployed near the OOI. It wasn't plugged into the OOI, but it was nearby, and so they could use their sensors and compare to the OOI sensors and get cross correlations between their data and our data. And we helped with taking push cores and doing other measurements as part of their project. All right, this is a rather new one. Tom saw this last week. This is a DAS, Distributed Acoustic Sensing project. So Ethan Williams generously let me borrow some of his slides. So seismology, oceanography, and bioacoustics using DAS. So this is a fairly new technology that actually turns the cable into its own sensor. So it basically converts optical fibers into a linear array of sensors. Using the strain, the change in the cable over time, you can see differences in the backscatter wavelength. So as you pulse laser light through the cable, the fiber optic cable changes shape over time, and as gravity waves and other waves impact the cable, and then that backscatter can let you basically turn this into a seismic sensor and an acoustic sensor. So they did an experiment where they sent long wavelength data down the cable while we had the cable active. Initially, they thought that we had to turn the cable off, so they could only use the dark cable to do this. But then they basically were able to acquire data on both lit and dark cable. So they used different wavelengths of light and were able to get their data while we were getting our data, and there was no interference. So yeah, there was no impact on our C-band communications while they were doing these DAS experiments, which is pretty exciting. And so yeah, we can now collect DAS information at any time without interrupting the observatory activity. And you can use this to look at gravity waves. Why is this? I keep getting too far away from the sensor. So yeah, the gravity waves apply pressure at the seafloor, and then that induces strain, and then you can see even shorter period wind waves and swell, long period infragravity waves. You can get seismic information from earthquake activity. There's tidal modulation of these infragravity waves. I am told that this is very exciting for physical oceanographers. So these infragravity waves are tidally modulated, and you can see reflections as these waves propagate towards the shore and then reflect off the beach, and they change. Some of this energy gets dissipated and some of it gets reflected. So you can use the DAS to study this. You can look at teleseismic earthquakes, so earthquake activity from farther away, and look at how these acoustic waves generate and propagate through the SOFAR channel. And it's been used for seismic ocean thermometry, which is a passive version of ocean acoustic tomography. And you can use it to listen to whale vocalizations. So they heard what did he say, tens of thousands of whale calls during the course of this experiment. And the experiment didn't last very long. And so it's pretty exciting that they can turn the cable basically into a hydrophone. And then this DAS experiment has now been folded into a recently funded project called COSO, the Cascadia Offshore Subduction Zone Observatory, which is a set of new technology, new geophysical sensors that are going to be deployed alongside the OOI and plugged into the OOI nodes. This is a multi-million-dollar funded project by William Wilcock and a couple others at University of Washington, APL, and Scripps. And so this will be coming soon. It'll be deployed, I think, for the first time in 2026. So this is an exciting expansion of the cabled array that will be used to basically address fundamental questions on how subduction zone faults work and provide a facility to support the development of offshore early warning in case of tsunami events or large earthquakes. So that's pretty exciting. And then we can also look at how OOI data is being used by people so for advanced data analysis, things like VARs that Mbari developed, and different types of automated video event detection. So a postdoc at University of Washington that I co-advised, Katie Bigham, presented some of this at the OOI Facilities Board meeting last week. So she's using machine learning and computer vision to help analyze the OOI imagery and annotate said imagery. So the goals of the project are to look at the temporal dynamics at Southern Hydrate Ridge, the methane seep community. There's over a decade of imagery, about 37 terabytes of data. These digital still images come from lots of different cameras. There's one stationary camera at Southern Hydrate Ridge, but there's 6 stationary cameras across the entire cabled array. They take 3 pictures every half hour. And so we're also using the ROV imagery from our yearly maintenance cruises. And she's using these to help develop machine learning pipelines to assist with processing these large volumes of imagery, which is exciting to me because when I was doing my PhD work, I was projecting film images onto an acoustic table and then poking it to determine where those sea urchins were going. And so using machine learning would have been very, very useful. So these are some of the still cameras. This one's at Hydrate Ridge. This one's at Axial Seamount. And there's a couple that are on those 200-meter moorings looking at the water column. I am not able to advance again. OK, so yeah, 6 still cameras. Like I said, they turn on every half hour and take 3 pictures, which gives us about 50,000 images per year, 2 to 3 terabytes per year, and that is adding up very quickly. So yeah, Katie's looking at the Southern Hydrate Ridge biology, including bacterial mats and animals. There's a large community of megafauna, including commercially fished species, so this is of interest to a lot of different people. That includes rockfish, hagfish, crabs. So initially, students were looking at these images and doing the annotation individually. Chris Moon is one of the UW undergrads who was doing this. And so when you do this, you get a set of data, and you can start interpreting, there's more animals in 2022. There's a lot of crabs here. More diversity in the spring. So yeah, you can start to pull out different types of information from this data. But they want to use artificial intelligence, the ability of a machine to mimic human intelligence, machine learning, which is a subset of AI, using algorithms and statistical models to perform complex tasks without human instruction, and then computer vision, which is a type of AI that uses machine learning to teach the computers to understand the visual data. So it's a process that you go through using these tools. And this is not unique to OOI. A lot of people are doing this, including people next door, Kakani Katija, and her FathomNet project for one. But there's a lot of different computer vision projects out there. And it's really exciting research. And it's not limited to benthic ecology either. There's a lot of water column experiments. So why is this so challenging? There's a lack of images to train from in the deep sea. There's a lot of computer vision projects that are using terrestrial imagery, and those can train up pretty quickly. But with deep sea biology, water can make things weird. The computer doesn't always recognize. If you look for crab images, you get a lot of surface crabs on a plate, crabs on the surface, crabs on the beach. you don't see a lot of deep sea crabs. And so OOI can help with this by providing some of these 50,000 images plus the image database that MBARI has collected and other sources to try to create these annotations using computer vision. So you can use this to do machine-assisted annotations. Nicola Jenkins is another student who's working on this. So this was using machine-annotated images. How have these habitats changed over time? So using ROV imagery. This was fully manual, so you run it, and then you go through, and it identifies objects, and then you go through and you say which is which, and then the machine can use that and train up and try to do better next time. So it took, with fully manual annotations, it takes 2 to 3 weeks to annotate 100 images. The machine-assisted takes about a week to annotate 100 images. And then if you take that process out, you can try to move towards fully automated annotations. So you you do some pre-processing on the raw data to try to make it cleaner for the AI to use. That applies annotations using the FathomNet model. And then you manually validate that and say yes or no, whether it's correct, put that into the training pool, and then use that to train, and then manually validate, and then create, using a localized version of the model, and then try to create a fully annotated biological data set from that. So another student at UW, Atticus Carter, who is super talented, it blows me away with his computer abilities, has been taking this 1 year of images, and it took 2 to 3 hours to produce this data set. I mean, there's still a lot of room for improvement in this model, but 2 to 3 hours versus 2 to 3 weeks of annotation. And this is much more than 100 images. So he's training a new version right now this week. And then they were able to expand this to track individuals. So you know that you're not counting the same fish 100 different times as this little rockfish stays in the same location over the course of weeks of imagery. Path tracking, where the animals go, how long they stay there. And then they're trying to use the ROV imagery and our imagery to create these 3D models of hydrothermal vents and how they change in space and time. So yeah, this allows for fine scale mapping of hydrothermal vent communities and how the behaviors change over time and how different parts of the vent are covered by different communities and how those sort of patches change over time. This is still in progress, so there's some artifacts in the video, but this is something that Atticus just sort of put together as part of his project. So I thought I would throw that in there. He's also working on some ocean computer vision tutorials that hopefully they'll be open access through Jupyter Binders and GitHub. Hope to launch in January 2025. He's teaching 10 undergrads in the winter quarter, and we'll be soliciting feedback and improving the course and notebooks. So if you want more information about this, just let me know and I can pass information on to Atticus. And he's going to be using ROV or RCA video and imagery to help with the course. All right, so all that said, we're also looking forward to see where we're going to be 100 years from now. We want to add vehicles, resident AUVs, and rovers and things like this to help us because the observatory itself is stationary, so it would be nice to be able to roam around these sites and see how things are changing, especially at dynamic environments like Hydrate Ridge. Adding new technology like stereo video, low light cameras, acoustic cameras. These have also advanced a lot in recent years. There's now these blue view sonars that can produce very high resolution imagery using high frequency sonar in very low light or high turbidity conditions, which would be nice to have at some of our shallow water sites where there's a lot of stuff being mixed up into the water column. Things like the environmental sampling processor developed at MBARI and now licensed for development. This is in situ PCR machines. This is a very old image. It's now been miniaturized and put into AUVs, but you can get environmental genetics, do eDNA experiments and things like that. So that would be fun to add to the system. And then different types of environmental experimental chambers and manipulations. People have added sediment traps nearby OOI to try to get more biological data. But you could also do different types of anoxia events next to the OOI instruments, so you have co-located data to go with your experimental manipulation. So anyway, there's a lot of different ways to propose experiments and propose new instruments to add to OOI, and the OOI management is very open to these proposals, and many, as you saw, have been funded over the last 10 years. So with that, any questions?
Okay, we'll take questions from the audience in the room, but there are viewers on Zoom as well, so I'll pass the microphone to anyone who has questions so that viewers on Zoom can hear your question as well.
For those on Zoom, Amanda is running to the audience.
Thank you. That was a really cool talk. So I personally have some experience with manually identifying inverts in ROV footage, which is a whole thing.
Yep.
But I was curious about like what proportion of the organisms are you guys able to identify at a species level, and like what proportion do you have to say like higher levels?
I would say nearly 0 to species level. It's really hard to do species level from imagery without having the organism in hand. But you can get pretty close if you know, because we can validate, and people have been studying places like Hydrate Ridge and Axial for a long time, and so they know roughly what organisms are there. And so if you know it's an organism that has been seen there a lot, you can get down to genus and species level, roughly. And so, yeah, rarer organisms take longer. You have to manually validate a lot of those. And yeah, so yeah, it's difficult. It takes longer for those. But there are, resident organisms that we know are there that are getting better at training the algorithm to catch.
Thank you.
Yeah.
We'll do Celine and then Nate.
Thank you so much for that talk. That was incredible. I feel like I learned so much.
Good.
I'm sorry if you already mentioned, but what was the reason that the Pioneer Array was relocated?
Right. I did not mention that.
Okay.
Good catch. So the Pioneer Array was always intended to be relocatable. That was part of the design of it, is that the array of moorings could be moved to new locations if the scientific community decided that they wanted a new set of data. Yeah, there were a lot of scientists that wanted it to stay right where it was to get the long-term time series there, because there was a lot of long shelf and different types of environmental parameters that they were looking at right there at Cape Cod. But they opened it up to the community and had a lot of meetings at AGU and Ocean Sciences and took comments from the community and basically decided that there was enough community support for moving it to the Mid-Atlantic Bight to do research there.
Thank you.
Thanks a lot. That looks like an incredible resource. I have 2 brief questions.
Sure.
Is there anything like this in California, or has there been?
Mars, the Mars cable array that MBARI operates
Okay.
is similar in some respects to the cable array. It was actually intended to be a test bed initially for the OOI, and then they sort of diverged on design, which some people are still upset about. Anyway, but yeah, so there's the Mars array, and they a lot of that data is open access. There's acoustic sensors out there as well as other types of sensors on there. Scripps has, there's moorings that have been out there at places like Scripps and places like MBARI looking at individual locations, but nothing quite on the scale of OOI in California, no. Okay. But Henry Rule at MBARI operates, he's the director of CENCUS, which is the Central California Ocean Observing System, and they have gliders that they operate. And so, yeah, there's the IUS program. That's the sort of the NOAA equivalent of the NSF OOI. And so there's a lot of different IUCE organizations around the country, including Sankus, Maricus, Nanus. They all have UCE in the end. But yeah, if you look into that, there's a lot of data out there like this.
Awesome, thanks.
Mhm.
And then I hope there's a positive answer to this, but what does the funding structure look like for OOI and similar projects, short term and long term?
Well, it's been nice to talk to you guys. Short term, everything is stable. We've been operating under a continuing resolution. There's no new budget. There hasn't been a new government budget for a long time, and so the continuing resolution continues funding at the current level, and that will continue for at least the next 2 years, I believe, all things being equal. And then the whole program is probably going to be recompeted again in 2028. That happens every 5 years, I believe. So NSF opens it up for new organizations to come and run different parts of the array and the management structure of the project. So yeah, hopefully we will continue to have a budget and funding. But the project is intended to run for 30 years, and that we've heard nothing to the contrary from NSF. They were present at the facilities board meeting last week, and yeah, I don't have any other information than that, but we'll see what happens, I guess. A tentative hand in the back.
Hi, really interesting talk. I liked it a lot.
Thanks.
I guess my question kind of relates to, in regards to like these, it seems like you guys are making leaps and bounds in deep sea observational technology, but do you think that possibly even like a network of cables and that outwards kind of compatibility could be worth creating a network in more of a shallow water scenario, in something that could kind of be a matter of unique bathymetry, just kind of to observe?
Yeah, okay. How to answer that? So yeah, there are some shallow water cable observatories in places around the world. Excuse me. There are cabled systems in the Mediterranean that are more shallow water. They're difficult to operate because in a lot of these things you need an ROV in order to plug things in. I guess if you were really shallow water, you could use scuba divers to plug and unplug technology, but it can be really challenging to operate and keep things operational when you've got wave activity and other shallow water processes. But yes, I guess the short answer is yes. The longer answer is it's tough to keep it running, but it has been done and will continue to be done in the future. Maybe not as part of OI, because the OI infrastructure is somewhat static. It's hard to add core pieces to this because, as was mentioned, there's a set budget for this, and so adding and removing things can be fraught. But yeah, we can compare and contrast the OI data. And there are parts of OI that are not cabled that are delivering near real-time data from buoys and gliders and other data sources. And so, yeah. I don't know if that answered your question, but
No, it does. That's
Okay.
all really cool. Thank you.
yeah.
Okay, one more from the audience here. It looks like we don't have any on Zoom. Any more in the room?
Slackers.
Hi, thank you for your talk. I think in one of your previous slides, there was something about like eDNA and PCR. Sorry if I missed this, but I was wondering if you could elaborate like what they're trying to find, and then are they like collecting data, and then to be like, will they like?
This is not currently on OI.
Oh, okay.
This is something that I would like to see added to
Okay,
OI.
cool.
But Mbari has put it on the Mars system, and they've added to their Gulper AUVs can take water samples and run it through this system. So if there's actually, I don't know if there's any Mbari people here, maybe online. Anyway, hopefully someone from Mbari will come and talk about the ESP, because Chris Scholin and other people helped develop it. And it's really cool technology. But they are looking at harmful algal blooms to see what organisms are there. They can do eDNA to see what, as organisms move through the environment, they shed bits of DNA, and so you can see what's moved through and try to correlate that. And you can look at bacteria, microbial communities. We would like to put one on axial to see whether the microbial community changes before and after an eruption event, because there's these sort of ephemeral snowblower vents that are just blowing microbes up from the sub-sea floor into the water column. And so that microbial community probably changes a lot as these eruptions happen. So yeah, things like that.
Okay. Are they like doing the PCR and like doing the sequencing like there, or are they like bringing the samples back?
It does it inside this device.
Cool.
So it's somewhat reagent limited, but it's pretty exciting.
Cool. Thank you.
Mm-hmm.
All right, thank you so much, everyone, for the questions, and thank you, Dr. Vardaro, for attending and sharing. We're going to continue. Oh,
I just wanted to say, so that the QR code will take you to the Data Explorer, which is our data portal, if you're interested. And you can learn more at the oceanobservatories.org site if you're interested in learning more about ocean observatories. Sorry,
awesome.
continue.
No, that's great. And also, Dr. Vardaro is available to stick around for a little while. So I'm not sure. I think the sun may have set already. Darn. But we could still go out there and enjoy. It's chilly, and just spend some time socializing and chilling, literally. So yeah, thank you so much.
Thank you. It was nice to be back. Oh no.
I know. We'll have to increase our